Okay, everybody, this is Brett Kinsella. I think you guys have come across me once or twice. I'm the founder of VoiceBot.ai. I'm really excited to be here today. We have with us Clinton May from Deepgram. And one of the things I think is really interesting here is that a lot of us got an interest in this space for the first time because of science fiction. And at this point, we're looking at something that's headed in that direction. So when we thought about voice AI and voice assistants, they started out in this more terrestrial version, Siri, Alexa, and those types of things. But now we have the opportunity to talk about a voice assistant in space used by NASA at the International Space Station. And that's why I'm so excited to have Clinton May from Deepgram joining me today. Clinton, why don't you come on up?
Hi, Brett. Thanks for having me.
Well, I'm really happy to have you here today. This is something that I think is near and dear to my heart. And one of the things I really like about this story too is it's interesting. People are interested in space, NASA, what are they doing? Extreme environments, constraints that you might not have elsewhere. But also every time I come across one of these seemingly novel use cases for voice AI, there's all these other lessons for the enterprise
for sure.
that just carry across. And you and I had a chance to talk about that a little bit. So I just wanted to go right into that. So Clinton, why don't we just start by setting up what was NASA trying to accomplish, and what were the key objectives that they laid out for you that you had to meet?
So there's been a bunch, right? There's a bunch of different voice cases, or voice use cases at NASA. And I think the interesting part was that we went to them and essentially said, and I still remember the cold call I gave to NASA. I had read an article that the CIO Ron Johnson had put out in FedScoop, and it said we're looking forward to AI to see if they can solve some of our communication problems, because the space to ground communications is so hard to understand. And I think that was where they started from, was that even for humans, it was difficult to understand what's being said. I've heard that when mission control in Houston, when ground control at Johnson Space Flight Center is listening to space to ground communications, people from the ISS talking to ground control, they stop and they take 2 or 3 of their people, stop what they're doing, and they write down on a piece of paper what they think is being said, so they can triangulate it later. So I think that why did NASA want to work with Deepgram? I think at its most basic was that they had really hard audio, and that nobody could do it. And they had tried, right? They'd looked at Google, IBM, Amazon, AWS, even the smaller businesses, and building their own. So they had invested a lot of work into trying to solve this problem. And I think that really goes to show that they care a lot about it, and they understand they've got, like you said, constraints, right? Unique constraints, difficult audio. And that's what I love to hear at Deepgram. I'd say if we do one thing better than the rest, it's the hard stuff. And I think that is the delta between the terrestrial series and stuff that you'd already listed. The speech recognition we're familiar with now, none of that can do really hard audio.
Right.
And NASA's about as hard as it gets. And I think that our win there and some of the expansion to other use cases shows what you can do with our new technology that you couldn't before. And I think that's the exciting part, right? Is taking it to the next level.
Okay, so this is great insight for folks. Most of our experiences have either been through the news media, which has some sort of broadcast from a space station, and you can see them talking to a television host or something like that live from the space station.
Yep.
Or we've seen, obviously, science fiction movies where the communication always seems pretty great. But you're suggesting that in most of these instances, it's actually garbled? There's a lot of noise. What is it that's the issue?
All those things. So it's tough. It's over a radio, right? That just makes everything tough. It's also an environment where you have to have high or near perfect accuracy or understanding, right? You really can't misunderstand what was said and then think that's okay, right? You really need to make sure that what's being said is correct. Of course, they've also got non-English or non-native English speakers speaking English. So there's all sorts of accents. It's the International Space Station, right?
Right.
And then sometimes you've got, when the space station is going around the world over and over again, it switches between a ground control in America and then a European ground control and then
Right.
the Japanese space station ground control. So there's lots of different languages. There's lots of different accents. There are non-native accents from one place talking to a non-native accent from another. All those things make it difficult. I think NASA's got the hardest audio for a bunch of reasons, not one, but those are some of the big ones.
And what about weather or storms in the ionosphere? Does that impact this as well?
I bet it does. And I think that's one of the things that we haven't quite gotten to yet. I'm not sure. I'd love to do some analysis on that. That's a really good question.
Okay. So, well, depending on the frequency, it might be a big issue or it might not be a big issue. So let's talk about this. So the first thing that they wanted to do was basically just have a clean transcript from an audio or from audio transmission, which is anything but clean. Is that correct?
Yeah. So I think that this is a point that translates to anybody in the industry, is that there are often pieces of information about what happened or why that are only available in the audio, right? So something happened, an incident, a procedure they were doing, and it didn't go well, or it did go well, and that information is in the audio. It's first in the audio, and if you can't extract it out of that audio, it's dead data, right? It's data, unlocked data is a cool way to put it. And I think that was the first practical use case that we went after. Was they wanted to search for previous incidents, but it's a huge amount of audio. They don't know exactly where it happened. If they wanted to search for patterns, they wanted to do aggregate analysis of what things went wrong over and over again. You can't do that unless you can get accurate transcription on all your previous historical, say, spacewalks. So that was a real practical use case. Let's build an accurate speech recognition, and then we can unlock our audio.
Right. And so what you're talking about isn't just the communication between ground control and the astronauts.
Yeah.
It's between the astronauts. There's a continuous recording of all of the conversations going on in the space station. Is that correct?
Oh yeah, and to mission control, and then with mission control to other mission control, right? There's mission control speaking just to each other, and that's tough audio too, because it's still over a radio. And it brings me to my last point about why NASA audio is so hard, is that even if the audio was good, the quality of the audio was good, there wasn't noisy or being spoken well, is that every third or fifth word that NASA uses is a made up NASA acronym. Right. Everybody who's ever worked for the government knows that they love their acronyms. And I think most enterprises have a problem with too many jargon words too. And if you can't get the jargon word, right, if you don't get the CBEF tool acronymed right, well, that was the whole point of what they were talking about. And you don't get the one word that indicates, what it was they were talking about.
Okay, so there's a few different things going on here, and I just want to break them down so that we're very clear with the audience here. So the first is ground control, when they're receiving a transmission from the astronauts, need to have a clean transcript, because sometimes they just can't make out the audio.
They always want another source of insight, right? Another guess.
And I assume that's bidirectional too. The astronauts probably have the exact same problem here in ground control.
Yes. Yeah.
All right. So now, does your solution provide the transcript on both ends?
It could, yeah.
Okay.
Currently, we're focusing on mission control, but absolutely could do the same for the astronauts on the ISS. Give them a live streaming closed caption of the conversation for sure.
Okay, and so that's automated speech recognition turned into a transcript. So that makes sense to me. Then there's this other use case, which is, you talked about ground control to ground control. What about astronaut to astronaut? If someone's on a space watch in the space station, is that clean because they're so close, or do they have issues as well?
it's still over the radio, right? Because they're not just shouting to each other.
Right.
So there's that problem. I have found from listening to a lot of this that they do okay with each other, but again, it's a stressful environment. You've got to get all the words right, and really, truly, every third or fifth word is high value jargon words. So, in my understanding, and I found this too from pilots and air traffic control. I think it's a real similar use case. They both need to know what was being said. They do readbacks. It's built into
Right.
the communication style and the only reason they do readbacks is to demonstrate understanding. To, hey, I heard you correctly. So in those kind of environments, you always want another source of the truth. You know, another person telling you you're right or wrong.
Now, the other use case is because there's all of this conversation back and forth, there's an opportunity there to identify things that maybe have come up that you missed. There are things that you can run analytics against that might help you in training or to avoid issues, or as I think you said, essentially audit incidents.
Yeah.
Because then you have all of the transcripts. Now, that's different than ASR. So you need the transcript, but you also need to be able to do the analysis. You talked about the fact that there's a large volume of this information. So are you doing all the analysis too? And if so, how does that model work?
So it's they're doing the analytics on top of our transcription, right? So every natural language processing group that has ever existed, it always does the natural language processing off the text, right?
Right.
And the mantra is junk in, junk out. So if you've got bad text, your NLP's not going to work. You can't trust it. All those things. So it was really the speech to text bottleneck, as I put it. Right? They already knew what analytics they want to do. There's all sorts of that stuff, but they can't do it until they get good text. And that was what we did for them. Nobody else could, and that's why they're expanding into all these different voice cases, is because now they can do analytics on text.
I think this is really interesting too, because Scott Stevenson, the founder, has been on the podcast. I've talked to him many times about the origin story here. And he originally created this system when he was 2 miles underground looking for dark matter to record the conversations he and the other researchers were having, so they didn't have to take notes all the time.
And so that they could go and find something that they'd said 3.5 days ago, maybe it was 2 days ago. Like, you don't know where it is, but you know what it was. And goodness, that is one of the first things I did for NASA when we were having those conversations and I was trying to sell them, right? It was a long time ago. I went and found a clip that I thought that they would know, but that they wouldn't have heard. And so if anybody on this call is familiar with the first American spacewalk, Gemini 4, it's a famous one. It's got its own Wikipedia article. But within that 4-day trip in space, there were a couple of big incidents that actually have their own Wikipedia page articles, right? That not just the spacewalk, but what happened. And one of those stories I knew, and that was when Ed White was on the first American spacewalk and having so much fun that he didn't want to come back in during his scheduled, okay, you're done now, you gotta come back in. And the space station goes through day into night, right? And so they're going into the night part, and if he's still outside, he's gonna maybe get stuck. So it was actually kind of a stressful communication between that group. And like, I'd heard that story. I think a lot of NASA buffs, I've talked to other NASA buffs, they know that story, right? So I went and found that clip. It's 4 days long. It's 4-day long audio clip of the first spacewalk. And I wanted to find the 2 minutes where they were getting yelled at by NASA to get back in the spaceship. And you can't do it if you've got bad ASR, but Deepgram went and found it, and then I showed that clip to NASA. I said, hey, NASA, you all know the story of Ed White not wanting to come. I said, yeah, we all know that story, but none of us have ever actually heard the audio. And I said, well, you know what? I found it for you, and I'd like to play it for you now. And that clip went over well. In fact, if anybody on the call wants to hear this, I actually have it queued up right now. Would
Oh,
Do you think the audience wants to hear
yeah, bring it up.
Ed White getting yelled at by Gus Grissom?
I want to hear it.
All right, all right. Well, let me share my screen. I got it right here. Okay. So just for context, this is Gus Grissom, who's at Capcom. Ed White is out in space, and then James McDivitt is the pilot of the spaceship that Gus is talking to.
The flight director says, get back in.
Jim, what, got any message for us?
Jimmy Ford, get back in.
Okay. Come over to the west end. They want you to come back in now.
Roger, we've been trying to talk to you for a while here.
No, back in. Come on. Come back in. 4 days ago, buddy.
So yeah, I think that was fun. It's you don't often hear NASA mission control putting some emotion in their voice, right?
That's right.
So yeah,
that doesn't get out there. That's
yeah,
not
exactly.
made for TV.
Yeah, yeah. And while this I think is a fun story, the real reason that NASA wanted to know where this was in that clip was because 6.5 minutes after the audio clip that I just played, James McDivitt is unable to close the hatch behind Ed White, and it becomes a really serious problem. They solve it, of course, but that's the kind of incident that NASA wants to go back and say, okay, what happened? What was being said? Where, you know, let's learn everything we can about this incident. But it's a 12-minute incident within a 4-day long audio clip. How are you going to find it?
Right.
Deepgram gives you timestamps, you know, per word. You find this clip, and now you know exactly where it is in the audio. So that was one of the first things that we did with NASA. I found some of their data that they didn't even know where it was, right? And I think that there's a lot of enterprises, a lot of companies out there who have a lot of data, and there's stuff in that data they know they want. But
Yes.
How are you going to find it?
This is an under-recognized value of voice AI that I'm starting to see more and more. There's a lot of places where there's continuous discussion. So you think about a contact center, and that part of the enterprise is much more likely to understand there's value there. Now, whether they can make any or they can capture any benefit from that is a different story, but they know that there is a lot of data there. This is the problem we see time and again, is that it's easy to search your text documents.
Yeah.
Even if they're in PDF form now, because we have really great OCR conversions, but in the voice space, it's not very good. This concept of search within is really poor. So it's not surprising to me that this is one of the interesting use cases. Now, I'm going to tell the people who are on today, we are going to take questions in just a few minutes. We're going to talk about a couple other things, including a medical voice bot. You can do a couple things. So first of all, there's a Q&A feature at the bottom. So just click that, and you can put it in the chat, but we might not see it. So you should just hit that little Q&A button and put your question in there. So we're much more likely to get to that. And you can, and if you do that, we'll make sure you get an answer one way or the other. Okay, so you have this transcript concept going, and that's a sort of a tried and true application of voice AI. There's a lot of times when the transcript is really useful and or necessary. And it sounds like in this case, it's probably both. But another thing has come up recently about this idea of having some sort of voice assistant which has medical knowledge. Mm-hmm. And so how has that happened today? Because I'm sure all these people are up there for a long period of time. Incidents come about, and from time to time, they need to have medical assistance. They're not necessarily a physician. Even if there were a physician, they're not necessarily qualified for whatever the problem is. And so today, if they have an issue, they probably have to call ground control to get help. Is that correct?
Oh, yeah. Yeah. And honestly, so even with the, say, in the future on the moon, it'll especially be even worse on Mars. The communication lag, right? How long it takes from someone there to talk and then answer a question and have it come back. It's not multiple minutes, but it's still significant. And NASA has really found that even a modest lag in that communication is going to be a problem in a lot of different scenarios. And so they've been looking at human to machine communication as you know, they're going to be out on different planets. You need to be able to talk to your equipment. And so there's a few different human to machine applications they're looking at, but the essentially the Hollow Doctor from AI from Star Trek is trying to be manifested right now. It's a real smart group at NASA who's trying to solve these problems, and they're a lot of fun to work with. But yeah, it's that's been an interesting use case that we've been working on a while now.
So that's going to be deployed directly on the International Space Station. Is that correct?
That's the goal, yeah. And then one day on the Gateway program on the Moon and Mars.
Okay, so let's think about what this does. So they treat it like a all-knowing physician and just ask it questions.
So that's the goal, right? And it's to get, I guess, triage is probably the best way to put it. What are the first things that you need to do, right? You need to, I need to stabilize the person, right? Okay, I've noticed these two things. That AI is going to say, okay, for those two things, these are the two things that you should do. So it's just it's a Hollow Doctor for real-time emergencies. If you can't wait, it's right there.
What are the type of emergencies, medical emergencies that occur?
Hopefully none, but all sorts, right? A crew member could be injured. There's definitely concussion protocols. There's definitely ones for heart attacks. You know, the common stuff, the emergency stuff.
Got it. So when they ask this assistant, it'll give them information. Does that conversation also get recorded and transmitted to ground control?
It could. This is still a little in theory now, but yeah, I mean, it should be.
Right. Yeah. So
they record all their audio.
That's right. And so when you're deploying something like that, this is not going to be a small language model. This is going to have to be a larger language model just because the medical domain is pretty large. Tell me about how you deploy it.
Sure. Great question. And I think it's unique to NASA, but it'll still show how other groups could use it. They got all of this stuff running on a Raspberry Pi with an external GPU. So Deepgram is one of the ways that we're unique is we're the true end-to-end deep learning, which means that we run on GPUs like way faster, like an order of magnitude better than everybody else. You know this, maybe some of your audience does too. But you could run it at scale better than everybody else. If you were doing millions and millions of hours of audio, you could do it at scale with us really well. Or if you're just doing that one transcription, the one person's voice to the AI, you can shrink that down and run it on a Raspberry Pi with an external GPU. I mean, you could hold that device in your hand, and it's also doing the analytics that NASA built on top of our speech recognition, right? It's not just hosting our speech rec model, it's also doing the natural language processing for the medical AI chatbot.
Is this installed on a separate device, or is this just part of the systems that are already there and it's just embedded?
So it's going to be on it's going to be its own thing. It's going to be a standalone Raspberry Pi with an external GPU, and that's the doctor.
That's really interesting. And will ground control have the ability to update it?
Oh yeah, yeah. And so
remotely,
that's one of the things that we've talked about, is being able to push those updates, because that's a limiting factor too. But that's while the language model, including a medical jargon, is a little bit bigger, Deepgram models are not as big and huge as some others. So I mean, it'll still fit, still did.
That's interesting, because you really think of something the size of the space station, you'd say, oh, well, you don't have the space constraints. You don't have the constraints in terms of processing power, but then you say, oh, well, that's actually not a very large space. And so you would think every centimeter is very important there.
And they have to leave half of that compute in reserve for emergencies, right? So they're only using half the resources they have up there, because this is NASA. You got to play it safe.
That's right. And you really need low battery draw.
Yeah.
Yep. Or low power draw. Yeah. So I can see how that's particularly interesting. So do you think there's a lesson from what you've done with NASA there? Because this is the idea of a completely autonomous medical voice bot, right? As opposed to a cloud-based voice bot. Is there a lesson here for how some of these solutions are being deployed on the terrestrial level? Because we have some symptom checkers out there, and we have some things. We've got some great success in the medical space about automated entry of data using these solutions, but there's not as much adoption around the symptom checker, beyond certain specific things like COVID.
Mm-hmm. Yeah, it's because Deepgram is fully end-to-end deep learning, right? In my experience, one of the great things about that is it's so easy to improve the model. It's so easy to train it to your particular domain. So I think one of the stories is that if you've got hard audio for any reason, but it's the same kind of hard audio, it's the same words, the same corpus of jargon, the same audio conditions in the background, any of that, it just takes a little bit of training data. That's fed to our model. The model learns it, outputs a new model that does better. And that method is really, it's pretty easy. It's efficient. We're really good at it. And all it takes is some representative audio that you have, label it, and then feed it to the system, and out comes a model that's really good on that. That's what we did for NASA. NASA gave us a list of 7,500 unique NASA terms that they expected to be in that audio. And they're in there over and over again. That's why the competitors can't do it. They're missing those words over and over again. We taught our system those words and how they sound in those conditions.
Right. Yeah, it's both.
Now it's got now it's got high accuracy, and now it can be used.
Well, so one of the things about Deepgram's architecture that always interested me is the initial deployment was this end-to-end, as you talk about it, deployment, where the ASR and the NLU work together in concert. They're not separate modules, it's one. And I think it's just one model doing both. Is that correct?
Oh, yeah. Yeah.
So does that provide higher fidelity for the NLU at that point? Because it's not just getting a truncated message of what the ASR thinks it is. It actually can see all the data.
Yeah, I think so. Because if you're going to do it if you're going to use a separate NLU and it's based off of the text could be wrong, and then your NLU is wrong. Deepgram, it isn't just based off the text, right? So we're a neural network, and we can understand examples. We can understand new data from previous examples, right? And that could be lots of different things, not necessarily just the words that are being said. So that's why I think it's a little higher fidelity.
Are you running one voice model at a time, or are you have you experimented with running multiples at a time and then looking at the responses of them?
Oh, you could, yeah, you could absolutely do what you just said. Because of NASA's particular constraints, we want to run just the one model for now, but you can absolutely run multiple models.
Okay, great.
Yeah, so doing it at scale, why not run a couple and see what's better?
So let's just talk about, before we get to the questions, let's talk about this idea of the end-to-end versus the discrete element type of architecture. And it's not necessarily a problem to have these ASR separate from the NLU, separate from the dialogue manager. That provides a lot of flexibility. And that's what most of what people have used from a voice assistant standpoint would be familiar with, or a transcription from that standpoint. But how do you do this where you actually put them together? What are some of the things you think about in terms of boundary constraints, benefits, handling the model differently?
Sure. Could you ask me the question again? It's a good one. I'm just trying to think it out here.
Yeah, sure.
Maybe in a different way.
So tell me how you need to think about the model differently if it's an end-to-end model versus plugging together at ASR, NLU, all the other components.
That's a great question. So the first one I think of is, don't worry about a denoising layer, right? I've heard NASA put in a lot of work trying to build denoising layers at the source. And then they did some experimentation with us and realized they should not build a denoising layer, and they should just use Deepgram, because Deepgram, when it has the examples with the noise, it understands what that word is in the noise's context. So it learns the holistic view of that word, as opposed to when you denoise use a denoising layer, it sometimes messes up the models downstream, right? That's what some folks have found. So that's one of the things is, don't worry about denoising, give us the tough audio, we'll just train on it. And then it's the improvement in accuracy too. If you want to teach new vocab, it's just training data, right? Just same as the noise stuff. So anything that you want to do to improve this model, it's the same method. It's just more training data. What we found is that those models are more flexible. People spend less time fixing one model and then having to fix another model because the change had unexpected consequences. Yeah, I'd say that's what I've heard from my customers and prospects. They're saving time because they're not having to mess with models, and they've got a good model that works, and that's what they do now.
Okay, so in the denoising, essentially they're trying to give you a cleaner audio feed to work from, but by doing that, they're taking out elements of the audio that your model can learn to use to improve accuracy.
That's a really good way of putting it. Yeah.
Yeah, that makes complete sense to me. So the last thing I was interested in is if you think about an end-to-end solution versus a more traditional architecture for a voice AI model, how does that impact latency?
But that's our favorite part. I'm glad you brought it up. At scale, we can do on a big enterprise GPU, we can do a tremendous amount of streams, at sub 1/3 of a second latency. Even on that Raspberry Pi with the external GPU, if you're just doing the one voice, that was, maybe 1/5 of a second. I'll have to check my notes, but it wasn't much. And that was, of course, one of the things that you have to have. So those end-to-end models are so clean, right? It's just that neural network. There's no 4 or 5 other models that it's got to go through. That's where you get that latency back. That's where you get the instantaneous, near instantaneous, actual real-time transcript, and that you absolutely have to have for a voice bot. No, it's 2022. Nobody's going to talk to a computer that has to think for a while about what you said, right?
Yeah. Also can be really useful in transcription if you're trying to do like real-time communication.
Oh yeah, because that's what closed captioning is, right? You can't wait a few seconds, right? You're watching that thing, you want those words essentially as they're being said before they finish the sentence.
So before we go to the Q&A, and anybody who wants to ask a question, just put it in there using the Q&A feature. Can you give me an example of let's say a corporate enterprise type of project that you've done since working with NASA, where you're able to take a lesson from what you learned working at NASA and apply it?
I've ended people's denoising projects. I'll put it that way.
Sure.
Right? They had an extant one that was going on, and I convinced them not to. Yeah, that's we've got a couple of deals. Maybe I'll close here real soon that I'd like to name, but I'll hold off on that just now. I'd say it always ends up being the acronyms. The FAA, right? So the FAA has, and this will be my last story. I know there's great questions. The FAA has the same problem that NASA does. All those pilots talking to all those air traffic controllers using a made-up language, right?
Yes.
Own made-up language over a radio, bad audio. There's foreign accents, and if you get a readback wrong, right? An air traffic controller tells a pilot descend to 2,000, turn left, bearing 180. The pilot says, I will descend to 200, turn left, bearing 180. Did anybody hear my readback error? Did you?
I did.
What if you hadn't? What if that air traffic controller said, okay, tell me how it goes? You can't do that, right?
Yeah.
So we're taking the same lessons there, and we're bringing them to the FAA, and we're going to solve that problem too.
Yeah, and you think about the phonetic alphabet that they use. Are they saying November in terms of a date, or are they telling you that N is the next letter? There are so many challenges that they have in that space that it seems like an obvious parallel, and I think there's many more that we'll get into at some point. We see that certainly in the contact center, where you have transcripts from people calling in from places where it's hard to hear them. Sometimes people call into support because they're actually in a rural or remote area because they need help and the signal isn't that clear. So I can see where something like this could be really helpful to, providing support as well.
Yeah.
Okay. So before we get to Q&A, Clinton, why don't you just tell people where they can learn more about Deepgram, what they should be doing next, how to get in contact with someone if they've got interest in follow-up.
Sure. So we've got an awesome website. If you're a technical person, go on there, make a free account, make an API call, see how fast it is, see how accurate it is, all that stuff. If you want to talk to one of us, you can through the website. And my encouragement is that if you think that your audio is too hard and that nobody can do it, give us a chance. Let's unlock that tough audio. That's my ask. Yeah.
Okay.
Cool new things.
Perfect. All right. So check out Deepgram online and you'll get most of it there.